So here we're investigating how neural circuits can link behavioral goals with the actions necessary to achieve those goals. To investigate this question, I have trained mice on an odor-guided spatial choice task, in which we can observe activity related both to the goal formation as well as the activity related to acquisition of those goals. While mice perform this task, I record from the intermediate and deep layers of the superior colliculus. This is a midbrain structure that is known to mediate both the selection and acquisition of spatial targets. However, few studies have actually examined how these circuits in the colliculus may combine these two processes, and that is what we're attempting to do here. So first, I looked at neurons that were choice selective, and I looked at their activity during that movement epoch. And I found that in my population, neurons that are choice selective increase their activity during the movement epoch, which suggests that these two processes are linked at the neuronal level within the colliculus. I next looked at how activity unfolded in these neurons as animals oriented to the target. And I've sorted these neurons based on the timing of their peak activity. As a population, it appears that these neurons can track where the animal is in space as in time or space as they are approaching the target. I next wanted to see if the timing of this maximum activity was dependent on where this neuron or where these neurons were recorded within the colliculus. Previous studies have observed a caudal to rostral shift in activity as animals acquire spatial targets. And this is based largely on the functional topography of how spatial targets are encoded within the colliculus. In my population, I see that rostral neurons are more active towards the end of the movement compared to caudal neurons, which is again consistent with what has been seen previously. So we next wanted to see if intrinsic mechanisms within the colliculus would be enough to reproduce this rostral shift in activity that we see during movement. We used this rate-based attractor model that we had previously developed to investigate choice mechanisms within the colliculus to test if a rostral spread of activity could be mediated by intrinsic SC circuits without additional input from external sources following the choice. We were able to reproduce this activity when rostral inhibitory neurons had a greater synaptic range than caudal inhibitory neurons.